So the next section is going to be solutions by substitution. So in this section, we're going to learn technique to substitute some variables so that we can have kind of, simpler differential equations. And we're going to talk about two different approach. The first one is one with let x equals to vy or y equals to ux. And then second one is called Bernoulli's substitution. And in the very specific form of the differential equations, by inspection, if it's in its form, then we can use Bernoulli's substitution. That way we can have easier approach to solve that differentially. So in this substitution, we compare dx terms and dy terms, and you identify simpler term and use either x or y equals to this. Then use the chain rule, dx equals y dv plus v dy, or dy equals dux or u dx. So that's the kind of key, and then solve the differential to separation. So let's work on this problem. So we have x equals to vy or y equals ux. Let x equals to vy. Now using the chain rule, dx equals first derivative and second one plus first, second derivative. Then the original differential equation is going to be x equals to vy. So vy plus y dx y dv plus v dy plus x is vy and then dy. Distributed vy times y dv plus vy v dy plus y dv plus y v dy plus vy dy equals to 0. Every single term has y, so we're going to multiply 1 over y for both sides. So then this is dv term, and this is dy term, this is dy term, this is dy term. So we're going to collect dv terms together, dy terms together. So for dv, vy plus y dv plus v squared plus v plus v dy equals to 0. Y b plus 1 dv, b squared plus 2b dy equals to 0. Now we're going to put v terms together, y terms together. So we have v plus 1 over v squared plus 2v dv, if you divide everything by this guy, plus for the y term, we have just 1 over y dy equals to 0. If you take the integral, y terms 1 over integral of 1 over y is a ln x. However, for the first term dv terms, we don't have anything like this in the cheat sheet. So we need to do the partial fraction in here. So for this term, I'm going to write v plus 1 over v plus 2. And we're going to separate this. So a over v plus b over v plus 2. And if we can separate these two, then it's going to be all ln terms when you take the integral of this. As you learn from the partial fraction, we can multiply these two together, denominator, and then numerator, a times v plus 2 times a plus b times v. Now the numerator has to be equal to the original equation. So when you compare numerator v1, v plus 1 equals a plus b, b plus 2a. Now we know a plus b has to be 1 and 2a has to be 1. Therefore, a equals to 1 over 2 and b equals to 1 over 2. So now the equation is 1 over 2 times 1 over v plus 1 over 2 times 1 over v plus 2. This whole thing of dv plus 1 over y dy equals to 0. X plus 1, x plus 2. For example, something like this, we can separate that. How? We'll call partial fraction. So we let this equals to a over the first product term, x plus 1, and plus b over x plus 2. And then if you have the force them to have the common denominator, and then a term, what is missing? I do have x plus 1, but I don't have x plus 2. So I need to multiply x plus 2. For the b terms, I do have x plus 2, but I don't have x plus 1. So I need to multiply x plus 1. That way, if we separate it, we end up getting this one. If this equals to this, then has to be equal to this. So now just looking at the numerator. The numerator for the left-hand side is 1, and numerator for the right-hand side, we have x plus 2 plus b, x plus 1. So 1 equals ax plus 2a plus bx plus b, and 1 equals, I'm going to collect x terms together, a plus b x plus constant terms together, 2a plus b. When you compare left-hand side, right-hand side, there is no x. Therefore, this has to be 0 and this has to be 1. So now we have a plus b equals to 0, 2a plus b equals to 1. If we subtract negative a equals to negative 1, a has to be 1, that means b has to be negative 1. So go back, we put this equals to a is 1 over x plus 1. So b is negative 1 over x plus 2. So now if, let's check this is correct. So if I make this to have the common denominator, which is multiple of these two denominator, for the left one, should have x plus 2 minus x plus 1. X will cancel that out. We'll end up getting 2 minus 1, 1. So it's the same thing. Why we do this? Can you take the integral of this? No, because it's too complicated. Can you take the integral of this? Yes, it's just ln x plus 1. So if we have a multiple of some two terms at the denominator, when you can separate them so that we can get the easier for the integral or multiplication. It's what we call partial fraction. It's really handy, and you need to be familiar with this because we do use this partial fraction all the time in Laplace transform. Now we can take the integral everywhere. Okay, so we have 1 over 2 ln v plus 1 over 2 ln v plus 2 plus ln y equals to c. And initially we let x equals to vy, right? X equals to vy. That means v equals x over y. So I'm going to put it back, v equals to x over y. And at the same time, we're going to multiply everywhere times 2. That means now we have ln v equals to x over y plus ln x over y plus 2 plus 2 ln y equals to c1. Now, we need to combine these all ln terms. One of you asked me about this, the power. So I went over log kind of property last time. So this guy is going to go up, and they are all ln and additions. If we combine them, they're going to be all multiplications. So if we combine ln, we have x over y times x over y times square. Then ln, put x over y inside of the parentheses, x squared over y squared plus 2x over y, and then y squared ln x squared plus xy e